when we look at redox reactions or redox reacties, ek het nou klomp keer vandag gesê in Afrikaans is dit lekker om te hou en in series die stroom dieselfde en sulke stupid goed wat dit lekker maak om te onthou. As ons na die redox reaksies gaan kyk, dan is dit eintlik makliker om dit in Engels te onthou. So nou by die Afrikaanse mense die Engelse rympies onthou. Makes it a heck of a lot easier. When I look at the difference between oxidation and reduction, it's all about electron transfer. When you look at acids and bases, it's all about proton transfer. The proton being the whole nucleus of the hydrogen atom. Oordrag van protone, die hele kern van die waterstofatoom by sure en basisse. Dis hoekom ons dit protolyse noem. Terwyl by 'n redox reaksies gaan dit net oor elektronoordrag. So only all about electrons being transferred. When I look at the basics, and I keep re-asking them, and if they don't ask them, you need to use them anyway. The first step is always oxidation. It's like getting a gift for your birthday. You can't receive one if somebody didn't give you one. So the first part is always the giving, then the receiving. So die eerste stap van redox reaksies is altyd oxidasie. If I look at the oxidation, the O in the oxidation is the one that I need to remember, because oxidation takes place when a subject or an atom or a metal or whatever it might be gives off electrons. So in Afrikaans, so 'n bietjie lelike Afrikaans, oxidasie is die opgee van elektrone. So tipies iets wat dit sou gedoen het is iets soos 'n metaal. 'n Metaal soos koper sal elektrone afgee en koper 2+ vorm en 2 elektrone afgee. So that's an example of an oxidation half reaction. Ek moet dit 'n half reaksie noem, a half reaction, because it's only half of the truth. Oxidation can never take place without reduction. Oxidasie vind nooit plaas sonder reduksie nie. Albei moet altyd plaasvind. Another example of oxidation could be where I had an anion, and the anion already had an excess of electrons, 'n anion wat 'n oormaat elektrone het, kan ook die elektrone afgee en daarom 'n neutrale atoom word. Dis ook oksidasie. Goeie voorbeeld wat julle baie gaan gebruik, chlor-alkali industry, die chloralkali sel toepassing, dis een van daai series toepassings, is dit ook nodig. Dan sal ons van ons redox tabel af gekry het dat 'n chloor anion, maar nooit een van hulle nie, 2, because chlorine is the diatomic gas. Group 7's are all diatomic, alle groep 7's is diatomies, will give off an electron, each one of them gives off 1, but there were 2 of them, so they give off 2. And then we're left with Cl, which no longer has an extra electron, and they bond to each other to form chlorine gas. So that becomes Cl2 plus 2 electrons. Those are both examples of oxidation. Now, together with oxidation, we have to define what a reducing agent is. In Afrikaans, 'n reduseermiddel. A reducing agent itself is oxidized. So die reduseermiddel word self geoksideer and therefore allows another substance to be reduced. So 'n reduseermiddel word self geoksideer en daarom kan die ander ou gereduseer word. So if I had to go and identify the oxidizing agents in this example that I've done now, then I would say, great, I'm looking for the reducing agent, sorry, not oxidizing, the reducing agent. The chloride ions gave off electrons. The copper atoms gave off electrons. So they would be the reducing agents. The minute they are ions in group 7, the N falls away and it becomes an I. In groep 7, dan wanneer hulle ione vorm, eindig al die ione op IED. So it's a chloride of an Afrikaanse chloried ion, in Afrikaans obviously ion met 2 O's. Wanneer die gas gevorm het, then in English this will be chlorine gas. In Afrikaans sal dit chloorgas of dan net chloor wees. So please note the chloride, chloride, and then the chlorine, chlor. In the same way, if oxidation takes place with this, it would be the copper atom, in Afrikaans die koperatoom. En nadat oksidasie plaasgevind het, is dit die koperkation, in Afrikaans die C met 'n K vervang, die koperkation wat sou vorm. Daai som dan vir ons op wat is oksidasie en 'n reduseermiddel. Die volgende stap dan is om te kyk wat is reduksie. If I look at reduction, in Afrikaans na reduksie. And again, it's easy if we use the English part to remind us, and we use the re part, because reduction is the receiving of electrons. So, selfs in Afrikaans, as ek met my klasse doen, dan sê ek altyd vir hulle onthou, reduksie beteken receive, en dan kan jy dit vertaal na ontvang elektrone. In the same way, it means if we understand the oxidation, the giving off, then here we could say that reduction would be something like an oxygen atom receives 2 electrons to form an oxide ion. An oxide ion with the 2 extra electrons is a O2 minus. Or it could be something where there was already a cation, something like a silver cation, Ag+, which receives an electron to form silver. All of them were receiving because it was plus 2 electrons, plus an electron. Now in general, when we talk about something like oxygen, omdat suurstof ook diatomies is. Wie is almal diatomies? Stikstof, suurstof en al die kloriede, fluoriede almal onder hom, al die halogene. So dis N2, O2, F2 en almal onder hom en heel bo links waterstof. Who is diatomic? N2, O2, F2, they stand next to each other. Everybody underneath F, because it's all the other halogens, and right at the top left, hydrogen. In English, it's very easy, all the gins. If it ends on gin, it's diatomic. Hydrogen, nitrogen, oxygen, and the halogens. Almal wat eindig in Engels op gin is diatomies. Because of that, what I've written here isn't actually 100% correct, because I haven't shown that when I look at the oxygen, it was actually diatomic to start. So to indicate that it was diatomic to start, I should actually have O2, which means that there would be 2 of these ions forming. And if there are 2 of those ions forming, it means that I actually needed 4 electrons. So if I look at the reduction, the same way that I had with oxidation, a reducing agent, then over here I will have what is an oxidizing agent. Wat is 'n oksideermiddel? An oxidizing agent is reduced, allowing another substance to be oxidized. Afrikaans, 'n oksideermiddel word self gereduseer en daarom laat dit toe dat 'n ander stof geoksideer word. In other words, the oxidizing agent is the one who actually receives the electrons. Die oksideermiddel is die stof wat self daai elektrone gaan ontvang. Met ander woorde, die oksideermiddel is die suurstofatoom of die Ag+ kation. And the next thing that goes along with this is understanding how, when we use the two different types of cells, how do we decide who's an anode and who's a cathode? And there's a lot of confusion about that. If I look at the basic definitions, what I'm writing down for you now is true always. It's an easy way just to remember. In English, it's a dog and a cat, but an ox. Remember the word an ox. And remember the word red cat, which is now written in blue, but never mind. Okay. As simple as that. Reduction, reductie, which means to receive, ontvang, elektrone, always takes place at the cathode, non-negotiable. Reduction can never take place at an anode, no matter what type of cell you've got. Don't ask me whether the anode or cathode is positive or negative yet, want dit gaan verander, dit hang van jou cel af. Maar altyd, reduksie, kathode, vas, nooit anders. The next one that we then have to go back to is at the anode, only oxidation can take place. By die anode kan net oksidasie plaasvind, nooit enigiets anders nie. En oksidasie is mos die opgee, the giving off of electrons. Now, if I remember that, and if I look at my redox table, it's very easy to determine who's the anode and who's the cathode. Now, on the table that I gave you this morning, the data sheet, they give you the table that you can use, the redox table, and they have changed it. In the past, they gave 2 redox tables. They now only give you 1, so you now no longer have a choice of which one you would like to use. If you're using old GDE papers, it's a slightly different one. It has 1 or 2 which aren't on here, and this has 1 or 2 that aren't than the others, but the concept works the same. Please ensure that you use the one with lithium at the top. Maak seker dat jy die een, as jy het uit 'n ander boek uit gebruik om te oefen, dat jy die een met lithium bo het. So as jy jou Doxenta boek deurgaan, ek het meeste van die werk wat ek daarin verduidelik het verduidelik van hierdie tabel af, omdat meeste mense hom gebruik. But there are times where I will refer to the other table as well, so ensure that you know that you're working from the top one. If you can't remember who's at the top, look who's second from the top. It's me, K for Corin, so it's easy. If you've got K for Corin second from the top, you've got the right table in front of you. Right, if I go and look at my table, the first thing you do in the exam, you pick up your table. This is yours now, so you can scribble on it immediately. The first thing that you will always do for me when you get your table is, and I'm just going to write down 4, because these are the 4 that I normally use, or maybe I'll make it 5, that I normally use to explain all this with. So say, for example, I look on my redox table and I look a few from the top, you will find Mg2 plus 2 electrons, reversibly forming Mg. A little bit below that, you will find Zn2 plus 2 electrons, reversibly forming Zn. A little lower at 0, you will find 2 H pluses plus 2 electrons, reversibly forming hydrogen gas. A little lower, careful for copper, there's stacks of coppers. Look at the one that's at 0,34. Remember the age 34? When you're 34, you have to have made it in life or you're never going to make it. Remember the 34? That's copper. Copper 2 plus 2 electrons, reversibly forming copper. And a little bit lower, Ag plus an electron, reversibly forming Ag. I like using those because they've got a whole lot of applications that I can use to explain the rest to you. You will notice that hydrogen is at 0,00 volts. Everything above is negative something, and everything below, the values for the standard redox potentials are positive. First thing you do if you get your exam paper is that on this paper, it's yours, write on it. Scribble on it, belongs to you. First thing that you're going to do is to indicate for me where the anode is and where the cathode is. It's something which is strong. It means it not only can, but it very often does, and does so well, and doesn't like doing the opposite. So if I tell you that magnesium is a strong reducing agent, it means it's easily oxidized and it likes staying oxidized. It means this reaction wants to read from right to left and it doesn't want to go back. If I tell you that silver is a weak reducing agent, ek wil sê silver is 'n swak reduseermiddel, beteken dit silver kan soontoe gaan, maar is regtig nie baie goed daarin nie. Hy sal baie liewer terug verander. So strong means I can and I want to and I want to stay. Weak means I can, I don't want to, I really don't want to stay. The same way around for the oxidizing agents. A strong oxidizing agent says I can and I want to, while a weak oxidizing agent says I can but I really don't want to. So ultimately, that is a stable substance and that is, that's unstable. It wants to change, wants to be there. Unstable, wants to change, wants to be there. Strong guys want to, strong guys want to. If I remember that, then when I go and I look at chemical reactions and electrochemical reactions are called that elektrochemische reacties. Are called electrochemical reactions because there is electric energy and there is chemical energy involved. And all these redox reactions make up electrochemical reactions. There are two ways in which redox can take place. Redox reactions can either take place spontaneously or non-spontaneously. Afrikaans, spontaan of nie spontaan. How do I know? I always have to start first with the anode and the oxidation, because you always give off first. If you have a substance, top right, remember I've said top, you don't say it in the exam, I'm explaining. Then I know that that substance is a strong reducing agent. Hy's regs bo, ek mag nie bo in die eksamen sê nie, maar ek verduidelik dit nou vir jou, so ek kan dit sê. As ek 'n sterk reduseermiddel het, lê hy regs bo. Hy sal definitief geoksideer word. Read it from right to left. Then move down until you get to the oxidizing agent, which will then be at the bottom and will be strong. It will therefore be the red cat, reduced at the cathode, and the reaction will be read from left to right. In other words, if I start top right, go across, come down, and go across. So it was top right, bottom left. I'm working with two things that are both strong. And then the reaction is spontaneous. It just happens. My cell phone's no longer plugged in. This morning when it fell off, it was. It's no longer plugged in. The cell in here has got a redox reaction taking place. Dis spontaan. Niks dwing hom nie. Hy doen dit self. In a spontaneous reaction, the reaction takes place without external energy. It just happens. As my cell phone weer pap is vanaand en prop ek hom weer in, dan verander dit in 'n nie spontane reaksie. In a non-spontaneous reaction, you always start on the right. Jy begin altyd regs. So, in a non-spontaneous reaction, the anode, which is oxidized, is a weak reducing agent, reads to the left. Then you go up, because step one is always on the right, the oxidation. And at the top, there is a red cat, which is a weak oxidizing agent, which reads that way. For the bottom one that I used, or the left, sorry, for the spontaneous, vir die spontane een, het ons geen extra energie nodig nie. Vir die spontaan, no external energy required. It just happens. For non-spontaneous, energy is required. So if I go back and I look at my redox table and I look at two substances and I want to decide whether or not those two substances are going to react spontaneously or not, I can do the following. Say I tell you that I had magnesium that reacted with silver plus to produce magnesium 2 plus and silver, and to balance it I needed a 2 there and I needed a 2 there. I want to know if that is spontaneous or not. Then I pick up my redox table. On my redox table it looked as follows: Mg2 plus 2 electrons, reversible Mg. Lower down it had Ag plus, electron, reversible Ag. I identify what was on the right and what was on the left. On the right was the magnesium. On the left was the Ag plus. That guy is a strong reducing agent. Dis 'n sterk reduseermiddel. Want hy lê bo. This is taken directly from the table. This guy is a strong oxidizing agent. That's how it lies on the table. And the minute it's strong and strong, I say this reaction is spontaneous. It's just going to happen. You don't have to force it. On the other hand, I could have had a similar situation where they ask whether the following, these are normally in the multiple choice and then the applications of the cells, where they can ask me something like, I had silver and I had copper 2+ ions. Now I have copper and I have silver ions. Same as just now, ended up with silver ions. Just now I used magnesium, now I've swapped it around a bit. 2 of those to balance it. To decide if it's spontaneous or not, I look at my redox table, I find the position of the copper and the silver. On your redox table, it looks as follows. Copper 2+ plus 2 electrons reversibly makes copper. And lower down, silver plus an electron reversibly makes silver. I look at the 2 reactants on the left-hand side and I find them on the table. On the table, I see that the silver lies there. I see that the copper 2+ lies there. Always start on the right-hand side. If it's at the bottom, you're not allowed to say bottom. It'll be a weak reducing agent. Omdat hy onder lê, ek sê net nie onder nie, is hy swak reduseermiddel. Maar ek begin altyd van regs af lees. En daarom is hierdie 'n swak oxideermiddel. Lees altyd van hierdie kant af soontoe. En daarom sal ek sê, hierdie was nie spontaan nie.